So the answer for this first one, why does length matter? Why is it directly proportional? More length. It's not an L. More length means more distance to travel. So if I have a pendulum here hanging from some hanger or something, okay, here's my pendulum. Here is equilibrium. So it'll go from one side to the other. Make some path like this. If I make the pendulum longer, you're going to make that green part longer. And it's going to have a longer distance to go. So that's why length does matter. It's got a longer distance that it's got to travel, so it's going to take more time to do that. Okay? Good. Jorge, what about mass? Why do you think mass did not matter? Okay, so it affected the momentum. What do you mean by that? Something. Sounds good. That's all right. Any other ideas? Why do you think mass does not matter? So talked about momentum. That's a good starting point. Why do you think mass doesn't matter? Sydney, what'd you guys say? Why do you think mass doesn't matter?
It's still going the same distance, so the weight of it doesn't really matter.
We're, if you want to just join that group there, we're just talking about the Notes 1B that I gave, or Notes 1B I gave you all last time. Okay? All right, so it still has the same distance to travel, so it doesn't have any further to go. Adding the mass is going to add weight to it. That's going to add inertia. But we talked about the momentum. That's going to give it more energy. It's going to give it more momentum to balance it out. So the reason why mass has no effect is because it does not change distance. And it increases inertia and force by the same amount. Or you could also say energy too, if you want to think about it that way. Okay, increases energy by the same amount. Or you can say the force. So having more mass means it is harder to move, but it has more weight in order to move it. It's kind of the same thing as what we talked about. Why do all things fall at the same rate? They all fall at the same rate because gravity increases, or the force of gravity increases to balance out the mass increase. Okay, same thing here. All right, last one, amplitude. Sam, what did you guys say about that one? No? All right, let's talk about amplitude because this is easily the weirdest one. So we said that length does matter because more length means it has a longer distance to travel. So amplitude, you start with some shorter distance. Okay, start with some short distance to travel. But then if you pull it back further, you've got a longer distance to travel. And yet we said that amplitude doesn't matter. Literally the exact same thing happens as in length, but amplitude doesn't matter and length does. Any ideas? Why would this thing not matter, but the other thing did? Answer is energy. The difference between length and amplitude is while length increases the distance to travel, it does not increase the energy it has. If you pull it back further on amplitude, you actually do increase the energy. So the reason why length does matter is because more length means more distance traveled without more energy. The reason why amplitude does not matter is because it has a longer distance to travel, but it does have more energy. So, you need to know all three of these. You need to know all three of them. Why do they matter? The first one is the easiest one. Pull it back further, or have a longer string. It's got further to go. That one's easy enough. Okay? Mass is also not too bad. Just remember why we said all things fell at the same rate. It's the same idea as that. Amplitude is the tricky one, so you want to make sure you're careful on that one. Again, the key for amplitude is if you pull it back further, it has more energy. If you do the same thing with length, it does not have more energy. Okay? Alrighty. Next one. I want you to draw a little diagram for me here. We're going to make a pendulum. And we're going to draw 5 spots for the pendulum. We're going to draw out at some maximum amplitude. We're going to draw down here at equilibrium. We're going to draw another max amplitude out here. And then we're going to connect the dots with our motion. And I want you to label A, B, C, D, and E. So A is here. B is here. C is here, D, and E. Krishan, do you need a paper? No. You got one? Do you need a pencil or something? What I want to do is I want you to tell me the velocity at each of these spots. I want to know how fast the pendulum is going at each spot. You're probably saying to yourself, Mr. B, how on earth am I supposed to know how fast it's going in that spot? Well, I'm going to make life easy for you. I'm going to give you 4 choices for how fast it's going. And here are the 4 choices. It's either going maximum speed, the fastest it can go, or it's going 0, which is the slowest it can go, or it's increasing speed, or it's decreasing speed. Okay, I'm going to give you about 3 minutes again, and at your table, I want you to do the same thing you did before. I want you to decide what you think each of these things is going to be. So talk about it as a table. Decide what they're going to be. Obviously, because there's only 4 choices but 5 questions, you can use them more than once. It's not just like, it could be that like you just use 2 of them the whole time. It could be that you use all 4, but one of them gets used more than once. Any combination of things. I want to know at each of those spots, A, B, C, D, E, what's the velocity? Is it maximum? Is it 0? Is it increasing? Or is it decreasing? Okay? Go ahead and take a couple minutes here, see what you can come up with for each of those. All you got to do is write what each of these are, write each of them over here. All right, take a minute, go. So this is what it should look like. It should be 0 at A, increasing on the way to C, max at C, the fastest it can go. It'll slow down as it goes away, and then it'll be 0 at E. Okay. The other thing we need to know is restoring force. So we've talked about restoring force. It's the force that brings an object back to equilibrium. What I need to know is, what is the restoring force everywhere? Is it the same? Is it changing? What's going on with it? So we're going to do the same thing. A, B, C, D, E. And we're going to use the same diagram. Here's your A, B, C, D, E. But this time I want to know what the force is. Okay? And there's one more option. So the options for the force are max, 0, increasing, decreasing. Yeah, let's just stick with those again. If you think the velocity is constant, you'll pick max for all of them. Or not the velocity. If you think the force is constant, you'll pick max for all of them. Otherwise, decide what you think the force is doing. Is the force getting bigger? Is the force getting smaller? Is it staying the same? Is it decreasing, max, 0? What is going on with it? So do the exact same thing you just did, but this time you want to figure it out with the force. So go ahead and talk. That would be acting. So the first thing you need to know is restoring force is trying to get it back to equilibrium. So the further you pull it away, the more it's trying to get back to equilibrium. So that means at A, the furthest away from equilibrium it could be, it is max. It wants to be at equilibrium, so as it gets closer to equilibrium, it decreases. So that one is correct. At equilibrium, it wants to be there. So it does not need to exert a force, which means it's 0 at equilibrium. As it goes away from equilibrium, it gets further away, so it needs more force to do that. So that increases it. And at E, it's the largest it can be, because once again, it needs to get back to equilibrium, so it's max. Not bad. That one's tricky. What do you notice about 2 and 3? They're opposites. Yep, they're opposites. So, if you can figure out 2, you automatically know 3. They're just opposites of each other. So where the velocity is 0, you have the maximum force, which is why it moves. Where you have the maximum velocity, you have 0 force, because it's where it wants to be. And so on and so forth. All right, go ahead and go back to your seats for me. Take a little stretch on your way back.